Welcome back. All right, so let's take a look at a few examples with regards to kinematics. Again, just foundational examples. So here's the first one, and I'll do probably about 10 of them in here. So what does 5 meters per second squared north mean intuitively? So this is a good question to be able to ask. There's nothing really to calculate, but to get intuition behind these actual measurements is very important. So first of all, we do know that this is a vector because of the fact that we are dealing with a direction, and the direction is north. So we can, assume if you're going, north, south, okay, east, west, okay, so we have that. So that's, first intuition is, okay, so it's a vector and it looks like it's, in the north direction. Now, the other component in terms of the intuition is this. So we can break this down. So this means 5, okay? And now meters per second squared, we write this in shorthand when we are doing measurements of acceleration. And so now in this case, we would be accelerating, so either speeding up or slowing down. Now, eventually you might get into changing of directions. But in this case, okay, let's just stick to the speeding up and slowing down concept. And when you are dealing with that, the meters per second, if you just simply wrote this 5 meters per second, then you would get a sense that this is some kind of a speed, right? Now, because it's maybe north, you can say that it's a velocity as well. But 5 meters per second, you would have an intuition, okay, so I am moving at 5 meters every single second. Now, because of the squared, this means that, so I like to kind of rewrite this in this way in terms of intuition, that extra second, okay, we typically would want to be able to write it like this, but it wouldn't be very nice to write it. But this gives us much more of an intuitive sense. What this is saying is that every single second that passes by, our speed is going to be increasing by 5 meters per second. So if you were moving along, if you started at 0 meters per second, so basically you're at rest, then what would happen is that after 1 second, you would increase that speed to 5 meters per second. And if another second passed by, so one more second passed by, so that would be in 2 seconds, you know that you would be moving at 10 meters per second. And then another one, 15, and 20, and so on. So it is an increase. So the intuition is that the acceleration here, so yes, it is in the north direction, but the speeds are increasing by 5 meters per second every second. And that is what the intuition actually holds. All right, so that's one example for you. Here's another example, and it says, what is the change in velocity? So that's what we want to be able to find. So please don't forget, so change of velocity. So that means we're looking for the change of velocity, right, in this case. And because it's velocity, I'll put a little vector symbol up on top. And that is always equal to the actual change. So in this case, they're giving us the initial velocity and they're giving us the final velocities. Just be careful here because of the fact that, so notice one is south, one is north. So we're going to have to write it with regards to the same direction. It doesn't tell us which one, so I'll do it in both. Okay, so let's assume that, we want to make it north. We'll find out what the answer for that is. And then once we have north, we can, of course, negate it, and then we'll know the symbol for the south as well. All right, so with regards to this is always your final velocity vector minus your initial velocity vector. This is just simply by definition of the change in velocity. So you would simply just state this as, so I'm going to keep north as my direction at first. So this is going to be meters per second, so keep it at north. Now this is going to be minus. Now because the other one is in south and it's 14.1 south, then I would have to actually negate it if I wanted to make it north. So that would have been negative 14.1 meters per second north. So now everything is north. And with regards to this, obviously these two, so that's going to be a positive right there in terms of the vector. So 0.81 plus 14.1 and that's simply 14.91 meters per second north. And because we want to kind of stick to significant figures correctly here, so this has 2 significant figures. The other one, so this one has 3 significant figures, so I'll just round it to 2. We typically take the lowest amount. So this is going to be 15 meters per second north. All right. And if you wanted to write this in terms of south, then this would be simply negative 15 meters per second south. So these two are equivalent. So either or will work for the answer for this one. In this example, we want to be able to find the acceleration of a particle. So that's what we're looking for, which has been traveling at 18.2 meters per second east and accelerated to negative 1.5 meters per second east in 18.5 seconds. So luckily, in this case, we have both of these in the same direction. So that's always something we want to make sure is true. So both are in east. And now I can take a step back if I want to find what the average acceleration is. Okay, so within here, then what we would be able to do is simply take these. Now, notice that it's starting from here. So this would have been my VI. Okay, so that's my initial velocity. And then it's ending over here. That would have been my final velocity right there. So you can write those as your given pieces of information. And then you can just utilize the formula. So in this case, this is the change of velocity, right here. And this is going to be over the change in time. Now the change in time is 18.5 seconds right there. So I have all of those pieces of information. You can write down the givens, right? So VI, VF, okay? And this would have been your delta T. So those are all your pieces of information. So I'm going to just write that. Maybe I'll do that over here just to pick them off so that you have them. So VF, all right, is equal to negative 1.5 meters per second east. My VI is equal to 18.2 meters per second. Notice the directions are the same, and also the actual units are the same, meters per second. And then your delta T is 18.5 seconds. So now that you have all of this, you can plug it all back into here. So this is going to be VF minus VI, right? That's your delta V. Okay, so that's the first one. And then divided by your delta T right here. So if I substitute everything back in here, so negative 1.5 meters per second minus, this is going to be 18.2, and that is also meters per second all over delta T, which is 18.5 seconds. So notice all meters and seconds right there. So that's what we want to be able to find out in this question. So let's write that out. So negative 1.5, 18.2, so that's negative 19.7 divided by 18.5, and that's going to give us negative 1.064, etc. Now I have to be careful, so rounding this, the smallest amount between all of these measurements is 2 significant figures. So I'm going to just write this negative 1.1 meters per second squared. Notice that the second and second, okay, will be second squared, and this is with regards to east. All right. If you wanted to change it back into west, this would have been 1.1 meters per second squared west. All right, so that would get rid of the negative for you. But this is what you would have, okay, in here. So there you go. That's what you have right there. All right, okay, so that's another example for you. In this example, we have a droplet of blood, and it has traveled 120 centimeters in 18 seconds. Then what was its average speed in meters per second? Do we know the direction of the droplet? Well, The second component, do we know the direction of the droplet? No, they do not give us any directions whatsoever. These are all just scalar values. So it looks like we just have distance and then we have the total time. So we won't be able to find any vectors in here. So no, the answer to that first one is, okay, do we know the direction? The answer here is no. Now for the second component, let's write down. So I'm going to maybe put down the given pieces of information. So what I actually have been given is I do know the distance, right? So this is the total distance that I have. I'm not going to put a vector there because it's not a vector. This is 120 centimeters. Oh, notice that they want meters per second. So this, the prefix from centi back to meter, right? So this is going to be just 1.2 meters right there. And then the other component is, I guess we have the change, and that is 18 seconds right there. Now we want to know what the average speed is. Okay, so with regards to the average speed, so this would have been just simply v, right? Again, no vector on top of that, and that would just simply be the change, okay? So this is the total distance that we would have, and so that's what we would have in there. And I guess I can put the delta here in terms of the change, and then this would have been just the change in t. So this is just straight from the definition, but they're not vectors in here. So I would have had 1.2 meters all over, and then 18 seconds, and I can obtain exactly what that is, because they do want it in meters per second. So 1.2 divided by 18, okay, so that's what I have. Now, let me just check. So two significant figures in total. So it's going to be 0.067 meters per second. And we do not have a direction in this case. All right, so that is it for this one. Here are actually two examples. So I'm bringing these two together because they're tied in. So the first example says that the acceleration caused by gravity is 9.8 meters per second squared down. So we have a direction, it just means down. Now, if you notice that an object changed its velocity from -2 meters per second down to 14 meters per second down, then how long did this change take? Now, the words how long means that we're going to be looking for time in here. All right, so we have an acceleration, right, that's given. We do have the initial and final velocities that are given. So that means we're just missing our total time. Now, in the next component, what's interesting is that they ask us, what does the -2 meters per second down actually mean? All right, so this is kind of important and pokes at you if you do understand vectors in general, right? So, and explain, draw a visual path. So I'm going to tie these two together so that I can answer both questions at once. So first of all, if I write down the given pieces of information here, then what you would have is you have an acceleration. Now this acceleration is, I'm not gonna write average there. It is an average acceleration, and it is 9.8 meters per second squared, and it's down. So we're making down positive in this case. All right, so that's what we have right there. Now, the other components that are given, so we know our initial velocity. So it says the object changes its velocity. So notice it's -2.00 meters per second down. And then my final is equal to 14 meters per second down. So I want to just kind of draw this whole thing out in here. So, make an actual diagram. So if we were, and now this is some kind of an object, right? So let's assume that the object is maybe some kind of a ball. So what it's saying is that you're starting off right there with this initial velocity. But it's negative, right? So if you think about what the negative vector means, this is actually nothing else but simply 2.00 meters per second up, right? So the direction just changes because the negative, okay, is going to negate the actual down. So this is actually up. So what it's saying is that this particular object is actually moving in this direction first. So it is moving in this direction initially. Now, as you know, if you have an object and it's actually trying to go up, I mean, unless you keep, pushing it upwards in some way, it's going to kind of just go up and then it's going to start to come down, right? So gravity is going to start to pull it down. So what's going to happen is, this object kind of is going to do something like this. And here, what they're saying is that this, okay, initial, so that answers your question right here. So this one, what does it actually mean? It means that it's actually going upwards in the beginning, and then drawing the visual path. So this is what's going to happen, okay, to this object. And then eventually what happens is that this particular object is going to be moving at 14 meters per second. Now notice it is down over here. So eventually it just starts to go down. And they want to know, how long did this actually take? So from, going 2 meters per second upwards, kind of stalling back and then falling back down. And, how long does that process take? And so here you would have to go back and think, okay, well, what is the average velocity? Maybe I should just write here. Okay, so this is the definition. So by definition, we know that it's the change in your velocity over the change in time. And in here, so if I'm going to do all of this all together, there's going to be V final, right, minus V initial, right there, all over my delta t. Now, I know this, so this is 9.8. Notice everything is down, right? So down, I'm going to keep this down, keep this down. You have to keep those at the same direction so that you can plug it into your formula. So this would have been 9.8, okay, meters per second squared. All the other ones are in meters per second, so that's fine. So that 9.8 now all of a sudden becomes your initial one and final one. So the final one is 14 meters per second minus your initial. Now your initial was negative 2.00. And then this right here was your delta t. So if you do all of this, this is going to be 14. So this and this is going to be positive, right? So this is going to be 16. And then 16 all over delta t. And it is equal to 9.8. Now, if you want to be able to solve for that delta t, you cannot have it in the denominator. And so that delta t, so you can multiply it on both sides here. So like this. Okay, so this is going to be gone. And then you will just have 9.8 times, times delta t is equal to 16. And now you can get rid of the 9.8. So it's going to be divided by 9.8 in this way. So this 9.8 cancels, and then your delta t, so the total time, is going to be given to you. So now if you take this, so 16 divided by 9.8 equals to 1.632, etc. And this is going to be in seconds, so it doesn't take really that long in this case. And I'm just going to kind of glance back, so if all the given pieces of information, so it looks like we have two significant figures as our lowest amount of sig figs in the measurements. So you would just simply take this as 1.6 seconds. And that would answer your question. All right, that actually answers both questions. So you have the visual, the interpretation of the whole thing. So this was a really nice set of two examples to make you understand these vectors and then also get some intuition to what's happening here. All right, so that's it for this one. All right, so another one, an athlete moves at a constant speed of 8 meters per second. How fast would he cover 100 meters? Round to the 10th if necessary. Okay, so this one is hopefully a lot easier, so we kind of have to write down. Let's take all of these given pieces of information. So notice it's a speed, there's no direction, so this would have been just v, and it's 8 meters per second. how fast would he cover 100 meters? Well, so 100 meters, so that's just the distance, so that's the change in distance. That would have been 100 meters, so the units are fine, so everything's meters right there, and then we have a seconds for the speed. And now, if you wanted to be able to, find this, you certainly can use, formulas, okay, within here. So you certainly know what the speed equation should be. So speed is equal just to the change of the distance divided by the change in time. So for example, you certainly can use this from the definition, but you will also notice, okay, so from right here, if you want to know the delta t, so if you rearrange this, you can multiply both sides by delta t, you are going to find that delta t is equal to, in this particular case, so that will be the total distance covered divided by the v. All right, so you can rearrange this formula for that. And if you wanted to know how to do that, this is just simply equal to, this is delta d, okay, this is delta t. If you multiply by delta t on both sides, all right, so that will get rid of this. And now next, okay, you do not want that v, so you're going to have delta t over v, going to divide this now by v, and you're going to get exactly the equation that I just wrote. So this will cancel, and you're going to get this back. Now, you don't technically need the actual formula. You can just use the units. If you know about unit conversions, you can certainly do that as well, right? So you can take the 100 meters divided by 8 meters per second, and you'll notice that the meters will cancel, and then the second will come up on top. Now, plugging these things into here, what that means is delta t is equal to 100 all over, and this is going to be, I guess, 8 meters per second. And so now in this case, what do we have? So this is going to be a little tricky because of the fact, okay, that we have divided by 8. So this is going to be 12.5 seconds. Now the tricky component is, okay, that this right here only has one significant figure. So, if we round this to one significant figure in here, well, does it tell us to round? Round to the 10th. Okay, so if you wanted to round to one significant figure, the answer would have been 10. But rounding to the 10th right here, well, this is already to the 10th. Okay, so you can just leave it as it is. All right, so there you have it. So that would have been the answer to this question. Here's another example. So given the equation, so again, we're kind of back to the velocity equation. And we have two components, so part A and part B. So we want to be able to find, okay, what the average velocity is in kilometers per hour. And we do have a direction here, so this is what we want to be able to find. And we want to keep this to two significant figures, okay? So this is at least what they're asking us to do. So we have two things. So here it is. And then we have the second part right there. Now, notice that the units are supposed to be in kilometers per hour, and they do not give us the time in hours. They give it to us in minutes. But this shouldn't be really that big of an issue here for us. So given, so what do we have? We have delta D is equal to, and this is 14 kilometers. Notice this is south. So that aligns fine. And then the delta T is equal to 30 minutes. But we would want the 30 minutes. I'm going to just change it because 30 minutes is just half an hour. So that's what we would have there. Okay, so that's relatively simple. So now if you plug this back in here, so if you want to know what that is, so notice I'm just using the formula itself, so substitute it back in here. So 14 kilometers, and it is south divided by 0.5 hours. So this is actually going to be equal to 28. And kilometers per hour, and it is south. All right, so it's already two significant figures as the answer has it. All right, so that's it for the first one. Okay, so for the second one, for part B, maybe I'll change color. We are trying to find delta t. All right, so delta t, so what do we have in there? So let's write down the given pieces of information here. We have been told, okay, so here it is, this is equal to 10 meters per second. Now this is west. All right. Okay, so luckily the change in, so this is the displacement right there. So this is 1.5. Okay, so this is kilometers. Now we want this in seconds. Now notice the units have to align. So one is in meters, one is kilometers. So I'm going to just change this. So kilo, right? So I can change that because that prefix. So that's going to be 1,500 meters. And this is still west. All right, so that's at least the direction aligns, which is great, which is exactly what we want to be able to see. And now, so substituting all of this into the formula. So if you take this formula right there, I have this, I have this. So I can solve for delta t. So that's going to be 10. And I'm going to drop the units because now the units are all aligned. And this is going to be 15 all over. And then this is delta t right there. So that's what I want to be able to solve. So rearranging, so delta t is going to come up, right? So it's going to go up. You can multiply by delta t on both sides. And then you're going to have to divide by 10 on both sides, like so. And you'll get your answer. So now, so this right here is going to be 150. And that's all in seconds, right? So 1500 divided by 10 is 150 seconds. They wanted 2 sig figs, and this is exactly 2 sig figs. And that's it. Okay, so that's that example. In this example, we have the following equation, which is given. And I hope that this doesn't actually throw you off. Notice that it's your v final is equal to v initial plus your acceleration times delta t. Now, the first thing that I'll say is right here is that this comes from the actual definition of acceleration. So you can kind of cheat in this question because it says that you have this equation given, and then you're supposed to find what the average acceleration is in meters per second squared west. So that's the goal. So you can technically just use your average acceleration if you want it, but I'm not going to do that cheating. So I'm going to try to use this equation because it forces us to try to learn how to manipulate the actual formula. So notice we have v final, that's negative 25 meters per second east. We have v initial, which is 2 meters per second west, and then we have the delta t. Okay, so let's write all of these down. And as you're writing it down, notice we want this west, so I'm going to change all of these to west. So v final is equal to negative 25 meters per second. So that's what I have there. East, so if I want this as west, well, that's just going to be positive now. And that's what I want. So now it's west. V initial is equal to, so this is 2. And it is meters per second. This is already west, so that's great. And then finally your delta t, which is equal to 12 seconds. Okay, so now I'm going to plug everything back into here so to find out what I need. So because everything is west, we can drop the direction, so we know that our direction for the acceleration will be west as well. Everything is in meters per second, and also the time is in seconds. So that will align with our units. So let's go ahead and try to substitute all of this back in. So VF, so that's 25, is equal to VI, which is 2, plus, notice that's the acceleration, and delta t is 12. So I'm going to put, we like to write the number first. And instead, I'm just going to write little a. It's instead of writing the whole thing, okay, for the acceleration. So now we can solve this. Okay, so moving this over on the other side, so it's going to be 25 minus 2. That's 12a. This gives me 23, 12a. And now dividing both sides by 12. So to get rid of that, and we only will have, so notice this will cancel, and this will give us that acceleration is equal to, so 23 divided by 12. And now we wanted this to two significant figures. That's at least what they said. So this is going to be 1.9 meters per second squared west. All right. And now I'm going to put in the vector. Okay. And you can write average if you wanted to. And there you have it. Okay. So that would have been for this question. That is it. Okay. For this one. Here's our final example, okay, that I want to be able to do in this video. So given another formula, so this is the delta D, all right, is equal to, and then, so this is the displacement, right? So this is what we have in terms of the formula that's given. We want to be able to find the final velocity in kilometers, okay, so here, kilometers per hour north, okay. Now, provided, now we have several pieces of information given. So we have the delta D there. We have our initial velocity given. Notice this is north. The displacement is also north, and then this. So the directions are fine. So there's nothing to worry about there in terms of direction. Now the rest, so let's write this out. So given, we want the answers in kilometers per hour, so that minutes is not going to align. I'm going to have to change that, but I'll do that in just a moment. Okay, so we have this given. That is equal to 2.5 kilometers. This is north, so that's good. We have this given, our initial velocity. That's 10. This is meters per second. Ooh, this is not going to be good, okay, because it's in meters per second. The other one is in kilometers. All right, and then finally, so delta T, this one is 12 minutes. Okay. So you can tackle this in kind of different ways because the units are not consistent, right? And we want the final answer to be in kilometers per hour. So you can technically, you know, change everything into kilometers, okay, and into hours, so you can certainly do that. The other way, and because I only have one of them, right, so I have the kilometers, and then the other components, I can actually just change back. So you can use whatever units you want as long as you're consistent, all right? You can, for example, change the kilometers to meters. That way you're only going to be dealing with meters. You can change the 12 minutes to seconds, and then you'll only have meters and seconds. Now you might say, okay, well, then I'm going to get my answer, right, to that in meters per second. And that's okay, because you can then change meters per second to kilometers per hour. All right, so that's, you know, something that you can do. So I'm going to kind of start to change all of these items, and maybe I am going to just kind of begin, because this is very easy for me to change. So I'm going to just change this to meters. Okay, so that's what I'm going to do. So now I have meters. Here I have meters and seconds. And in this one, I'm actually going to change the 12 minutes. I'm going to change that to seconds. And then don't forget, you know, so 12 minutes. So I would have to multiply this by 60 seconds, right, per minute, so that the minutes will cancel. Okay, and so that's going to be 12 times 60, so that's 720. Just don't round anything here, and that is now seconds. Now the reason why I've done that again is because now this is meters, this is meters, this is seconds, this is seconds. So that aligns. When I substitute it back into the formula, that means that my velocity is going to be in meters per second. So I'm going to have to do a conversion at the end. All right. The directions are all north, so there's no worry with that. So now I can go ahead and start working on this question. So let's substitute it back into the formula. So if I take this and I write down the formula within and start to substitute in here. So my delta D, so that's going to be 2500, so this is meters, equal to my V initial that I have, so that is 10 meters per second. My V final is what I'm trying to find. I'm going to just avoid the vector here, so I know that it's going to be north. And this is going to be all divided by 2. And then finally at the end, my delta T is 720. All right. So now you might say, oh, this kind of looks ugly. I have to solve for this, right? So how do I, proceed with this? What should I actually start to do? Well, so one of the first things that you can do as you're solving for this, you don't want to have, okay, the 720. So what you can do first is divide both sides by 720. So that will get rid of this 720 from this side, and you're going to have that gone. Now, of course, that means you're going to have kind of an ugly number there on the left-hand side. So 2500 divided by 720, all right, which is going to give you this. Now, because you're not supposed to round in intermediate steps, I would just leave it as a fraction, okay? So within here, I would just simply leave it as it is, meaning I would just say, okay, so this is, sorry about that. So this is just 2500 over 720, and it is equal to, and now all I have is 10 plus VF all over 2. So that's what I have there. Now, I can see that I have a 2 in the denominator, so I can multiply this by 2, and multiply this by 2, and this 2 will be gone in here, and this will help me, right? So this 2, so 2 multiplied by this, so this is going to be 5,000. Now you can certainly reduce if you're comfortable with reducing, your fractions. I'm just going to leave it, okay, as it is, because I can let my calculator do the work at the end. And this is what I have up to this point. And now all I have to do is just move this 10 over on the other side. So meaning subtract the 10 from both sides. So that's going to be 5,000 all over 720 minus 10 is equal to VF. All right. So now let's plug that in. So 5,000 divided by 720. So now my calculator has this, and I don't have to actually write it down. I'm just going to take this answer and then subtract 10 from this, and this will give me my answer. So this is negative 3.05555. I'm going to just do a bar because these are repeating all the way through, and that's what my answer would be. And this is north, so that means the negative actually tells me that it's south. All right, so this must have changed the directions. Now, I just have to go back. I have to round this to 2 significant figures. Those are going to be negative 3.1. And this is meters per second. Okay, and I'll keep this north because that's what they wanted, right? So this is all north. And that would have been your final answer. All right, thanks for watching. I hope all of this was useful. Give it a thumbs up if it was. Bye, everybody.